So welcome to the lecture on application of Matlab in automatic control. So we discussed in previous lecture how to find the transfer function, find the poles, zeros, and how to get the response like step response, impulse response, or some arbitrary input response under some arbitrary input. So in this lecture we will continue the response of first order and second order system under step input, and then we will discuss about some steady state errors and root locus. So here we have this some of these problems, like how to plot the response of the following transfer functions. So we have these transfer functions like 9 upon s square plus 9s plus 9, and there is some step input because the rs of the step input, unit step input, is 1 by s. So how to find the transfer function? So here we can see that in the numerator there is the polynomial which has only one coefficient 9, and in the denominator we have coefficient 1, 9, 9. So we have to first find the system using tf, the transfer function. So if we know that tf command, we use tf num comma den in the parenthesis. So here num we will write only 9, and then here 199, and then we can find the response. So here we will first find the system transfer function. So system equal to tf. Now we define the numerator, that is only one coefficient 9, and then comma the denominator. So we will have 199. So 199. So and then parenthesis close. So here we have got this transfer function 9 upon s square plus 9s plus 9. So if we want to see the step response, so we say step sys. So here we can see the step response of this system. So there is unity step. So you can see here this is the step input 1, and the system response is reaching towards the step input. Now we want the pole of the system, so we can write pole sys, and we can get the pole minus 7.8 and minus 1.1459. So we see the poles are distinct, and because this is a second order system and the poles are distinct, we will get a response like what we got here, step sys. So this is the response that we will get. Now let's go for the second system, that is here 9 upon s square plus 2s plus 9. So here we have in the denominator 1, 2, 9. So here we put the system, we define sys. So here 1, 2, 9. So this is the system. Now we get the pole of sys. Here we can see that these are the complex pair poles, complex poles. So they are minus 1 plus 2.8i and minus 1 minus 2.8i. So they are complex poles, and if we have complex poles, then this system response against step sys we can find. And you can see here when the poles are complex, we have under damped system. So damping is less than 1, so between 0 and 1. Now the earlier system, when the poles were distinct and real, the system was over damped system. So here we have underdamped system, and we can see that this amplitude is decaying with time, and there are some oscillations. Now we take the third example. Here 9 by s square plus 9. So here we have in the denominator 1, 0, 9. So here if I define the system, I will say 1, 0, 9. So this is the system, and transfer function is 9 upon s square plus 9. Now if I get the pole of the system, pole says, I will get that here we have real part is 0 and the poles are plus minus 3i. So these poles are on the j omega axis, and so this is the case of critical damping, and this we will see the response of this system against step input. And here we know that when the poles are on the j omega axis, they have the oscillations, and we can see here the oscillations. And because they are plus minus 3, so omega is 3 here. So these are the oscillations because the poles are on the j omega axis. So here we find this s square plus 9 case. Now we have another problem, that is 9 upon s square plus 6s plus 9. No, so this case, that is 9 upon s square plus 9 is undamped case, because here we have the damping, that is damping is defined if we have a system like b upon s square plus as plus b. This is our gs. So our damping a equal to is a by 2 root b, and omega is root b. So here in this case, when we treat the case 9 upon s square plus 9, 9 upon s square plus 9, so we had here a equal to 0 and b equal to 9. So a is 0, so damping is 0, and b equal to 9, so omega n equal to root 9, so we were getting 3. So this is the natural frequency of the system, and this is undamped response of the system. So what we saw here, this is the undamped response. There is no damping in the system, so this is the natural response of the system with the natural frequency, that is omega n equal to 3. Now we come to the last case here, this one. So 9 upon s square plus 6s plus 9. So here s is 6 here, s coefficient. So we can write the system. Here is 6. Now we have 9 upon s square plus 6s plus 9. So we get the poles of this system. So we get the pole. So we get here the poles, the imaginary part is 0. Both the poles are on the real axis and they are equal. So this is the critical damping case, and if we see the response of the system, step says, so we will get this response. So this is the critical damping response. Now we come to the last case, that is gs equal to 50 upon s plus 50. So we have gs equal to 50 upon s plus 50. So we can see that this is a first order system because here the power of s is 1. So now if we want to write this in Matlab, so we define the system. So TF is 50 here in the numerator, and here we will have only s plus 50, so 1, and this is 50, and there will not be this term, so we have only 1 and 50. Now this is the system. So 50 upon s plus 50. Now we define the pole. So pole says that is equal to minus 50. Now we get the step response. So we get it. So we can see that this is a first order response here, and this response is leading to the unit step input. And if we take this cursor here, so we can see here amplitude is 0.62, and we define this as it is happening at time equal to 0.0193 or about 0.02. So when from this curve we can find the time constant, that is the response reaches to 63%, and so we can reach the time constant we can get about 0.02 second. So this is the response of the first order system. So here we can obtain the response of first order and second order system in Matlab. Now come to the another problem, that is the steady state error and the steady static error constants. So we have this unity feedback system, and for the given system we have to find the static error constants, and we have to find the error, steady state error for the standard input, that is step, ramp and parabolic input. So here we have this function that is 500 so s plus 2, s plus 5, s plus 6, and then s plus 8, s plus 10, s plus 12. So this is the GS of the unitary feedback system, and we have to find the static error constant and steady state error for step, ramp and parabolic inputs. So we know that this system is type 1 system, and we know that if the static error constants we have already defined. So Kp equal to Gs, s tends to 0, then Kv equal to s Gs when limit s tends to 0, and Ka equal to s square Gs. So these are the, and from here we find static error equal to 1 by 1 plus Kp we have already defined. From here E infinite equal to 1 by Kv, and here E infinite equal to 1 by Ka. So these formulas we have already discussed. So let's first define these numerator and denominator. So we have, so first we clean this screen, CLC, close all and clear all. So we clear the workspace and close all the figures, and then again we clean this screen. So now let's define NUMG equal to 500. So numerator we are defining with 500 into the polynomial -2 -5 -6. So we define this polynomial for numerator. So -2 -5 -6 into 500. Then denominator, so D and G equal to, so polynomial 0 -8 -10 -12. So this is, we have defined the denominator. Now we can get the transfer function G equal to TF num G comma then G. So we have obtained this transfer function. So we can see here G, if we enter G, we have got 500 SQ plus 500 into 500. So we have got this transfer function. Now we have to find the equivalent transfer function we can get, that is T equal to with unity feedback. So T equal to feedback we get G comma 1, so unity feedback, and we have got this transfer function. Now for the step input we want to calculate Kp. So here Kp equal to DC gain G. So what we are doing here, DC gain evaluate the Kp of G for S equal to 0. So DC gain command says putting just S equal to 0, because here Kp define S tends to 0 for GS. So this will be evaluated for S when S is tending to 0. So we will get Kp. Now we will calculate the steady state error equal to 1 by 1 plus Kp, 1 by 1 plus Kp. So okay, so we can see what is Kp. So Kp we have got infinite, because this is a type 1 system. So if we give the step input, we must get an ESS equal to 0. So steady state error 0. Now come to the ramp input. So for ramp input we have to get SGS. So we have to multiply S in the numerator. So we are doing this. Num numerator we are redefining nums G equal to conv 1 0. So this is a polynomial, that is S and 0. So that is just S 1 0, and we are earlier num G. So here we have con. So we have got S into the numerator of this GS, and then SG equal to same as earlier denominator, because we are not changing. So we can say then SG equal to deng. D, E and G, because it is the same, but we have just renamed another variable also with the same denominator. So then Sg equal to dang. So we have got, now we want Sg equal to tf transfer function num Sg comma then Sg. So we have defined S into G. So now we have obtained S into G. Now we have to put the limit S equal to 0. So by using DC gain command. So to get KV, so KV equal to DC gain Sg. So KV equal to DC gain Sg. So we have got, and ESS now equal to 1 by KV. So we can see what is KV. So KV equal to 31.25. So this is type 1 system. We are getting a finite KV value and we will get the finite error. So we are getting 0.032 steady state error for this system. Now we go for parabolic input. So parabolic input, we have to put S square G. We have to get S square G. So we will repeat this nums 2G equal to conv. So here we have 1 0 0. So it is just S square plus 0S plus 0. So S square, and you multiply, conv function multiplies this with num G. So we are getting the numerator for the parabolic input, and then dance to G equal to same as, because this is the same, so we can say dang. So we have got this. Now S square G or S2G, we say S2G equal to transfer function, that is nums to G comma dens to G. And so now we will use, here we can also use one more command, S to G equal to min real S to G. So that we forgot to use in the last part. So here min real command will cancel the common terms in the numerator and denominator, because we don't need those terms. They will, if they in the in the numerator there is suppose S plus 2 and in the denominator also S plus 2, they will be cancelled. So this command we have to use min real S to G, and once this we do, then we can get Ka. So Ka equal to DC gain S to G. So we get Ka, and then ESS, steady state error 1 by Ka. So you can, here we can see what is Ka. Ka we are getting 0, and ESS we are getting infinite. So this is how we have obtained this steady state error and static error constants for a given system. Now we come to the next problem, that is find the root locus. So we have to find the root locus for this. So we know that we have already discussed about root locus techniques. So root locus represents the movement of closed loop poles when we vary the gain. So we discussed several rules that may help us to identify the branches of the root locus and to sketch the root locus. However, in Matlab there is a very simple command that can plot the root locus. So we will see we have this system that is k s plus 3 upon s plus 1 So this is the this is our input and this is the GS and this is unity feedback. So this is our system and we have to plot the root locus. So in order to plot the root locus, okay, so first we see here this GSHS, open loop transfer function. What is this GSHS? So HS is 1 here. So GSHS is the same as this. So that is s plus 3 upon s plus 1 s square plus 4s plus 16. So this is GSHS. Now for this open loop transfer function, this is called open loop transfer function. We have this open loop transfer function, and so first we find the transfer function. So we define the num equal to 1 and 3, because this s plus 3 the coefficient are 1 and 3, then denominator then equal to, so denominator is equal to, we have some factor, so convolution we will use the multiplication of two polynomials. So first we take this s square plus s, so we will have 1 1 0 1 1 0 first polynomial, then we will have 1 4 16 the second polynomial. So s square coefficient is 1, then s coefficient is 4, and then the constant term that is 16. So 1 4 16. So we have, now we can define the system that is equal to TF transfer function num comma den. So this is the transfer function we define. So we obtain this transform s plus 3 upon s power 4 plus 5 s cube plus 20 s square plus 16 s. This is the transfer function. Now if we calculate the pole of the system, then we get these poles. So here we have 0, -1 and these two complex poles and zeros. So 0 cis so open loop poles and open loop zeros, so that is -3. Now if we want to plot the root locus. So we just simple command r locus num comma den. So this simple command will plot the root locus, and we can see here this root locus. So now I connect this with the theory. So we know that first we calculate these poles, and these poles we obtained here. We can see here these poles 0, -1, and then -2 ± 3.46 J. So these are the 4 poles, and the 0 was at s equal to -3. So now we can focus on this root locus. So I said that on the root locus we must first plot the sigma j omega axis. We plot the open loop poles. So here 0, -1, then here -2, so +-3. So these are here, these 2 poles, and there is one 0 at -3. So here at -3, this is -2, and here is -3, there is a 0. So we have 4 poles, and we know that here the root locus will lie in this region. So the root locus will start from here, and it should break away at this some point, and then root locus will not lie in this region. So odd, it will lie to the left of the odd. So 1, and then here we have 2, here it will not, but here 1, 2, 3, 4, here also not lie, but it will lie here, it will reach. So we can see we have 4 finite poles and 1 finite 0. So the one locus will reach to this -3, but others 3 will reach to the infinite. So how it will happen? So these are going to break away, and they are going like this. These 2 poles, they will start and they will meet, because they will move in similar way, because the 2 poles will be in pair, and one will reach to this and other will reach to the infinite, and they will reach to the infinite, and following certain asymptote, we can find that asymptote, and we can also find where they are cutting the j omega axis. So here we can see this thing. So these poles going here, then leading to the unstable region, and we can find what is this unstable region. We can see here that here we can find the breakaway point. So we can see that at gain 1.43 they are breaking away at -0.524 on the real axis. Now we can see here is break-in point, because they are getting here at break-in, and we can see that at -4.18 and at gain 189 they are breaking to the real axis. Now we can see this is j omega axis crossing. So here at gain 33.9 and here this should be 0, then about 3.16 of omega they are crossing to the j omega axis and they are going to the left. So the gain limit is 33.9. We can't keep the gain more than 33.9, otherwise they will reach to the unstable region. So here we understood how to find the response of second order system, first order system, how to find the steady state error under different inputs, that is step, ramp and parabolic of a given feedback system, then how to plot the root locus using Matlab, and how we can relate these plots with theory that is already discussed in the lectures, and we can get some insight into the quick insight into the problem. So I stop this lecture here and we will continue in the next lecture. Thank you.